Did you know that graph neural networks can learn to represent nodes in a graph with just 10% of the parameters of a traditional neural network, while achieving state-of-the-art results on node classification tasks? Here's what nobody tells you about graph neural network fundamentals and history. To understand the deep dive, you need to know the basics of neural networks and graph theory. A graph is a nonlinear data structure consisting of nodes and edges, and graph neural networks are designed to work directly with this data structure. The real story is different from what you might have learned in a typical introduction to neural networks. Graph neural networks have a rich history, dating back to the early 2000s, but they have gained significant attention in recent years due to their ability to model complex relationships between objects. Now, let's dive into the technical details. The core idea behind graph neural networks is to learn a representation of each node in the graph by aggregating information from its neighbors. This is typically done using a message-passing framework, where each node sends and receives messages to and from its neighbors. The messages are then used to update the representation of each node. One popular algorithm for doing this is the graph attention network, which uses self-attention mechanisms to compute the importance of each neighbor when aggregating information. The architecture of a graph attention network consists of multiple layers, each of which computes a new representation of each node by attending to its neighbors. The output of each layer is then used as input to the next layer. Here's some example code to illustrate this. Class graph attention layer, NN, module def _init_self, in features, out features super, graph attention layer, self, dot _init_self dot linear equals nn linear, in features, out features, def forward, self, x, adj attention weights equals torch dot matml, x dot t, attention weights equals torch dot softmax, attention weights, dim equals 1, output equals torch dot matml, attention weights, x, return output. This code defines a single layer of a graph attention network, which takes in a node representation x and an adjacency matrix adj, and outputs a new representation of each node. The attention weights are computed using a self-attention mechanism, which assigns a weight to each neighbor based on its importance. The output of each layer is then used as input to the next layer. Now, let's walk through a concrete example of how this works. Suppose we have a graph of users and their friendships, and we want to predict the interests of each user based on their friends. We can use a graph attention network to learn a representation of each user, which captures their interests and relationships with their friends. The real-world case study is the Pinterest graph neural network, which uses a graph attention network to recommend pins to users based on their interests and relationships with their friends. The model was trained on a graph of over 100 million users and 1 billion edges, and achieved a 20% increase in user engagement compared to a traditional neural network. This is what matters for you. By using a graph attention network, you can learn a compact representation of each node in the graph, which can be used for a variety of downstream tasks, such as node classification, link prediction, and graph generation. Here's an actionable tip you can try today. Implement a graph attention network using the PyTorch geometric library, and experiment with different architectures and hyperparameters to see how they affect the performance of the model. Don't forget to subscribe to HumanOverAI for more in-depth technical content.